Hello everybody, we will continue with lecture number 22, where we will talk about this different idea of solving optimal control problems, which is known as transcription method, and followed by generic philosophy we will cover, not too much detail into that, and followed by we will go to a very recently evolving concept called pseudospectral transcription. So, essentially it borrows the idea from transcription method, but it is a different way of putting the problem in the framework. So, the solution can be very fast, and hence the claim is it can be done in real time actually. Okay. So, that is a very recent thing. So, we will see the concept first, what is transcription method, and then slowly migrate to that, and then follow up with some problem solution and things like that. The topics are like this. First, you will see some motivation, and then philosophy of transcription method, which is very different from, well, what I am talking here is direct transcription actually. Okay. So, this direct transcription is slightly different from what you have seen before, and then followed by this pseudospectral transcription. We will demonstrate the idea of pseudospectral using a toy problem first, and then we will go to a real application problem and see how this is useful and all that. And remember, there are several problems which have been solved by different authors recently using pseudospectral and all that. So, we will not go too much into that. I will list out a few references also for your further reading basically. So, let us see the motivation first, and in a generic view, in a global view, optimal control formulation can be thought of something like this. One is indirect approach, one is direct approach. In indirect approach, we studied something like variational calculus approach, where it leads to this 2-point boundary value problem and all that. Whereas, in the direct approach, we have this dynamic programming, which we have already studied, and then we will have this transcription method, okay, which we are going to study today actually. Okay. So, alright. So, this necessary conditions of optimality through variational calculus, if you see, this is the idea that is developed actually. First, we have this dualization of the problem. That means, we have the state equation, but along with the state, now we assume another co-state equation, another set of equations with the same dimension, like lambda dot and all that. So, we have this state equation, along with that there is a co-state equation. There is optimal control equation, which is a stationary equation actually. Okay, if you solve it, we get the solution of control as a function of state and co-state. Then associated, there are boundary conditions and things like that actually. Okay, the initial condition is for the state, and the final condition, boundary condition, either it is given for the state or it comes to this transversality condition and things like that actually. Okay. Now, the question is, okay, we have gone through these difficulties and all that actually, that state equation develops forward, co-state equation backward, it is a split boundary condition problem, hence it is a 2-point boundary value problem, all sort of things actually. Now, the suiting method is one more method. So, before we have talked about gradient method and all that, but suiting method is something like this. The whole idea here is we have this initial condition of the co-state which is not known. So, we guess the co-state, initial condition of the co-state. Now, if you have initial condition of the co-state, then state and co-state equation can be propagated forward together with respect to that guessed co-state value at T naught. And then we see, okay, when t goes to Tf, your final value of lambda is somewhere here, whereas the boundary condition will give you something else, let us say that is here. So, utilizing this error, whatever error has happened, now we update this initial condition lambda 1 to, let us say, lambda 01 to lambda 02 and repeat the procedure. Maybe the next iteration it will go a little closer to that, and again even update further, it will go further close to that, and then finally converge here actually. That is the whole idea here. Okay. So, if you do that, then what happens is the difficulty is, because typically co-state equation happens to be an unstable equation, and you are integrating the equation forward. So, we have this sensitivity issue. That means, it is sensitive to the procedure and essentially to the initial guess value of the co-state actually. Okay. And typically the further difficulty is we cannot have a good guess of the co-state, because co-states typically do not have physical meaning, even though there is a little bit mathematical meaning. That co-state is nothing but the optimal if you have optimal cost already, then in dynamic programming sense, lambda is del j by del x, so gradient vector of optimal cost. But that does not help too much in guessing a number for the initial condition for the co-state actually. Okay. So, typically it is usually done through kind of a guess a control history, some heuristic control or non-optimal stabilizing control you use, and then use that, predict it, use that control from the initial condition of the state, both in the state sense. Remember, these are co-state trajectory, but you will operate on the state, then finally you will get a final state, and once you get a final state, you can evaluate this and then come back, integrate the co-state equation backward, and hence you get some sort of a information about lambda 0. Typically it is done that way. Okay, the whole problem is co-state equation is normally unstable, okay, and hence the long duration prediction is not good. Because anywhere there is an error here, anywhere there is, if you are not very close to the real optimal lambda 0, okay, then you will have this difficulty of error amplification very fast, because the dynamic equation is unstable actually. Okay. So, typically long duration prediction is not good. So, what do you do? We have to do this idea of divide and rule. That means, instead of predicting for a very long time, how about predicting for a shorter duration? Let us say T0 to Tf, I will divide it to two parts, T0 to T intermediate, Ti something, and then Ti to Tf sort of thing. Okay, so this approach is called something called multiple shooting. Okay, you split the duration into several segments like this, but when you do that, it brings the additional constraint that okay, around this point you have to make sure that this discontinuity doesn't come. I mean, this point kind of falls there, same point, as well as the derivative smoothness should also be there. The derivative over here should be equal to the derivative there, at least the first order derivative actually. Okay. So, these are some of the additional constraints that we will put into the problem actually. Okay. So, these are additional constraints at the joining points actually. Okay. But having said that, if you put these conditions intact and then try to solve it and things like that, it essentially leads to okay, this concept of transcription method. This is kind of a direct approach. In other words, if you think about kind of segmenting it to a large number of segments actually, then essentially it boils down to some sort of a discretized version of the problem. And hence, that is the approach of what is called a direct transcription method actually. So, this is philosophy of direct transcription. Okay, essentially, it converts the dynamic system variable into a finite set of static variables or parameters, and then pose an equivalent static optimization problem. Okay, and then solve the static optimization problem using this static optimization methods. And essentially, there are methods for this so-called nonlinear optimization or nonlinear programming basically. So, use that and then solve the problem for the static optimization framework actually. Then obviously, you have to assess the accuracy and repeat the steps if necessary, and there are concepts like fine tuning the grid points and things like that. If the coarse grid point is not good, you have to go for finer grid points, and that is called mesh refining and things like that actually. Okay. Alright, so this is the whole idea of this transcription method actually. Now, in mathematical sense, what is the thing? We have this objective of minimizing this, the notations are slightly different here, but essentially it conveys the same message. You have to minimize this cost function, which is a function of state and control both, which is an endpoint condition and there is a path condition subject to this dynamic equation, and with endpoint, this is the soft condition for endpoints, whereas these are hard conditions for the endpoint actually. Okay. Some endpoint conditions equal to 0 and things like that, some functions of endpoints, essentially they tells that okay, the desired value can be fixed, initial condition can be known, things like that. All these, everything will fall within this functional form if you write it that way. And there is also a path constraint which are not discussed so far, but we'll discuss one of the for subsequent lectures, where this problem can be subject to the state and control inequality constraints on the way basically. So, these constraints are also part of the problem formulation, don't forget that actually. Okay. So, this is how the problem objective is, and the whole idea here is we select a set of grid points, discretize the state and control variables, convert the problem into a nonlinear programming problem and solve that problem. And it should solve in such a, preferably we should solve that in a computationally efficient manner actually. Okay. That is what the whole idea, of direct transcription. So, to demonstrate the idea, what you are talking here is, okay, let us say assume that okay, time domain is discretized into the several points like that, here one, here one, here one, like that actually. And if you have a continuous function, like say x of t is some continuous function like this, what you are telling is, okay, we select the value of x of t at that point of this, and then here and like that. So, then you join it linearly basically. Okay. So, this continuous function is approximated by a set of straight lines, okay, or piecewise continuous function, you can see that way. So, essentially approximate the trajectory that way and discretize the state equation, okay, And also you can discretize the control variables as well, similar to state variable, you can do that also. Yeah. Then also we need an approximation of the integration of the cost function, and we will proceed that that is easy, but there are several improvements on that also basically. Alright, how do you mechanize this? This discretization of the state, you can very easily do that using this Euler's method. In other words, if you take Tk plus 1 is Tk plus delta t or Tk plus h sort of thing, then you get something like very easily you can have a pair of x naught u naught, x1 u1 and things like that for the entire domain actually. Okay. Euler method is very easy because it all tells x of k plus 1 is xk plus delta t or h, whatever it is, x. Okay. It tells that if you have a differential equation x dot is f of x, so let us say x of u or whatever, then xk plus 1 is xk plus delta t times fk of xk uk. Okay. So, that is very easy to see all that actually. You can implement that and have a set of finite constraint. This will act as a constraint now on those variables actually. So, the system dynamics is accounted for on the grid points basically in some sense. Alright, so this is how the way to discretize the state dynamics. So, we got a discretized form of the state dynamics using Euler method, let us say. So, this is what is written here, and in the matrix form if you put it there, then it turns out to be something like this, and the approximate the integration is something like this. Suppose you want to there is an integration that needs to be done, okay, this L, okay, and this is also like okay, you can think of this a small error here, to make it compatible you can think that this is not f, but this is L actually. Okay, so this is L. Okay, so you can, and all these are also like L basically. Okay. Anyway, so that is a way of implementing the trapezoidal rule really, but things may be different also when everybody does not have to use trapezoidal rule per se. But to visualize the concept actually, so you can see that okay, state equation I can discretize using Euler method, and cost function I will discretize using a trapezoidal rule actually. Then it becomes easy problem sort of thing, and the entire set of state equation what you see in the grid points can be written in this form, okay, in that side actually. The endpoint conditions also you can put x of t naught is if you put a grid point at the initial time and final time, then directly values are known to us. Then path constraints are also given. Okay, these are the path constraints that needs to be satisfied. Remember, all these things are now converted in the set of discrete form, actually, discrete variables really. So, everything will happen good in a discretized sense sort of thing. Okay. So, then you have a set of compatible optimization problem for the static programming sense. We have this discretized cost function to optimize, okay, subject to this equality constraint, and subject to this initial final condition constraint, and subject to this path constraint. Everything happens in the form of discretized variables actually. So, now we have a compatible nonlinear programming, and hence we can excite any of these techniques which are available, numerical techniques and all that, to solve this problem actually. Okay. And just to recall, somebody can think of utilizing this MATLAB optimization toolbox and things like that actually. Okay, there are toolboxes, there are various other toolboxes available in the market as well other than MATLAB, but MATLAB also has this fmin_con function and all that which I have discussed before. Those things can be excited to have a solution of these discrete variables. Remember, you are not solving a continuous optimization problem, you are solving the discretized optimization problem really here. Then there are various ideas about that. So, how to do the better approximation of the state dynamics. Euler integration is not good. You can think of higher order finite difference. You can use the RK4 methods, RK methods, RK2, RK4, things like that. We can use polynomial approximation in segment, the Hermite polynomial and things like that. Coming to the better approximation of cost function, you can use higher order approximations, or you can think about using quadrature approximations as well. These are mathematically more powerful actually. Okay, you can also talk about finite element approaches nowadays and many different variations around that. Okay. So, in general, one can think about improving the accuracy using higher number of grid points, okay, and then there is this indirect transcription method, okay, which is always there with us, which is going through this dualization of the problem through this lambda dot equation, and then using some sort of numerical procedure for that. And that's really indirect. So, we are talking about direct transcription method here. So, that's not that much relevant here. But ultimately, remember, even if you go for indirect transcription, what you are getting solution is for the grid points only. So, that is our restrictions, let us say. Then coming to the computational efficiency point of view, people can think of using sparse algebra, because if you see this matrix, okay, lot of zeros are there actually, okay. So, because of this lot of zeros are available, is appearing naturally, why to do 0 computations? 0 into 0 is 0 all the time. So, then this sparse algebra can be excited to speed up the algorithm, and then also you can excite this mesh refinement ideas, okay. So, this first you solve this with a coarse grid, minimum number of grid points being less, you solve it, and then increase the number of grid points, and then subsequently increase it further, then things like that. So, that is the idea of mesh refinement actually. So, initially you will not waste too much of computational time, and for working directly with some sort of a coarse, some sort of a fine grid point. Lot of grid points means large dimensional optimization problem, and you do not want to run into this difficulty of large number of local minimum, and then issues like computational time and things like that. So, it is always advisable to start with a coarse grid and then go slowly towards more and more number of grids actually. So, that is called mesh refinement. Okay. Many references are available based on this whole idea of direct transcription, and you can see many of these first thing that probably comes to my mind is this seminal paper which comes in 87, and then a little more better explanation sense and different problem and things like that appeared in 92, which made it little more headway. And then there are several other papers available, and like let us say this survey papers, and then the more elaborate explanation and things like that available. You can see some of these, especially the last one is also a very good one. In fact, the author has written a book, and he has also developed a commercial software for solving industry grade commercial software for solving optimal control problems using this direct transcription approach actually. So, you can see some of these concepts out there. Especially you can concentrate on these page numbers, about 15-20 pages, where you can get a lot more insight into that actually. Okay. Anyway, let us come back to that, and as I told in the beginning, we will concentrate on a different approach which has evolved recently over last 10 years, I will say, which has become very popular in aerospace industry, especially in USA, because of several practical problems they have applied, and then it has also been tried out in International Space Station zero propellant maneuver, and several satellite minimum time maneuver and things like that actually. And now it has also been applied for reusable launch vehicle guidance applications, and it has also been used in robotics, collision avoidance, things like that actually. So, there are many things that are happening recently. So, I thought okay, it is a good idea to see this philosophy, so that if some of you are interested, you can develop some affinity towards this, and probably you can think of that as a possible research direction for yourself also basically. Alright, so we will go back to the problem definition, and then come back with this objective. We have to minimize this cost function with the soft endpoint consideration. This cost function contains an endpoint endpoint function and a path dependent function actually. Subject to this the system dynamics with endpoint boundary conditions as well as path constraints like this. The philosophy here is discretize the sets same as before, as well as the control. Now, using pseudospectral method. So, we do not have to put blindly grid points and then try to discretize it directly sort of thing. And what is pseudospectral, I will explain in next couple of slides anyway. So, we have to discretize it, but discretize it in a different way using pseudospectral method, and so that you can convert the problem to a very lower dimensional nonlinear programming problem. So, the whole idea here is how to formulate a lower dimensional LNP problem actually. so that it can be solved much more faster. Okay. And while solving, you have to solve in a very computational efficient manner. So, various branches of mathematics will come together here, and essentially it will put together in such a way that ultimately it results in fast solution basically. Okay. So, let us see steps involved for this particular thing. First of all, you have to approximate x of t and u of t, but how do you do it? Something like this. You do that. Remember, this pseudospectral method is largely inspired from these solutions for partial differential equations also. So, the one way of solving partial differential equation is through basis functions and all that. So, you use basis functions in one dimension and then leave the other dimension for converting for PDEs to ODEs and all that. Probably that concept we will see towards end of this course in 1 or 2 lectures. But then we will right now borrowing the similar philosophy, what we do here is first we approximate this state and control using some sort of basis functions phi n, okay, which is phi 0, phi 1, phi 2 and things like that. And these are typically it can be polynomial basis functions, for example, power series and all that. That is not very effective. So, the study tells us that in function approximation theory, if you go to that side of the story, there are better function approximation basis functions like Chebyshev polynomial, Legendre polynomial, things like that. They are essentially kind of power series, but terms taken together and things like that actually. Okay. So, more on that you can study some math book. Legendre polynomial, Chebyshev polynomial, things like that actually. Okay. So, if you have that kind of thing, then we take a bunch of those. And remember, those polynomials have a nice form of recursive relationship. So, in other words, programming sense also it can be very fast actually. Okay. So, you go there and then tell, okay, x hat of t is something like this, x hat is n and u hat is v n, something like that actually. So, these are written like that in a finite number of basis functions. This dimension can be different. For simplicity of algebra sake, we will take it something same, but here it can be n1, here it can be n2, it does not hurt actually. Okay. Then you have to select a set of grid points anyway, okay, and I will will summarize how to select a set of grid points actually. Okay, now how are these points selected, and that becomes some sort of a question. And then obviously it turns out that uniform grid point is not a very good choice. So, we would have to opt for some of these so called non-uniform grid points for, see, the whole idea is how to represent the same problem in a less number of grid points actually. So, a large number of grid points is not a choice. So, we want to have as less as possible, and it turns out that we can really do a good job with less number of grid points, but we have to compromise this idea of uniform grid point. We have to go through this non-uniform grid point, Gauss collocation points and things like that actually. Okay. So, this now discretize the differential equation using pseudospectral method, and that method turns out to be something like this. We have this finite difference pseudospectral versus pseudospectral thing. Okay. That means finite difference is typically not good. So, what you do is this differential equation, we do this spectral discretization sort of thing. So, essentially instead of running into a large dimensional sparse matrix actually, what you are looking for is a small dimensional dense differentiation matrix. What is differentiation matrix? Is something what we studied just now, this form. This is called a differentiation matrix, if you see that actually. Okay. So, this can be defined as a differentiation matrix. So, instead of a large differentiation matrix with lot of zeros, sparse matrix, what you are looking for is some sort of a similar matrix which will do a similar job, but we want a smaller dimension yet a dense matrix. We do not want to see zeros everywhere actually. Okay. Alright. So, now we have to do this approximate the integral equation also, and that can be done using this quadrature rules for better accuracy and all that actually. Okay. Now, we have to use apply this efficient finite optimization. After that also we are not done, remember that. Even though you have represented it as a equivalent smaller dimensional problem, still that smaller dimensional problem has to be solved as fast as possible. So, you have to use this algorithms which has to be very powerful. Also remember that whenever there is a processor capability of whenever there is an increase of capability in the processor, that also comes very handy actually. So, in other words, going to this computational advantage of modern day computers or modern day processors, things like that, that also comes very handy. But it's not the entire solution. Solution lies really in the good algebras actually. I mean, sorry, good algorithms really. Okay. So, you have to opt for something, some better capable algorithms to solve this NLP problem, and always solving that on an onboard processor which is more capable is always better actually. Okay. So, this is how the whole idea is there, and I will explain the steps little more clearly here actually. So, how do you do step 1? Step 1 is approximation, right. So, how do you do approximation? Now, this approximation needs to be done in such a way, so that the residual between these two, whatever norm of that, needs to be small actually. Okay. Now, how do you make sure that that is small? So, what you do, this is already the approximation we have, and now we define some sort of test function, some other different functions, that chi0, chi1, chi2 like that actually. Okay. Alright. So, in such a way that it is, well, this is chi1 basically. Okay. Alright. So, this is, we have to do it in such a way that this residual error has to be minimum. Remember, this is the inner product, an inner product of continuous function. In other words, integral sense actually. So, this inner product is defined something like this. You have two continuous functions. Okay. So, if you have two continuous function f1 and f2, then the inner product between them is some finite interval, let us say 1t, then 0 to t. Okay. Then f1 of t and f2 of t dt sort of thing. Okay. So, that is what the inner product definition is. That is what you are using here actually. Okay. Alright. Now, the question is, you have a test function series, but what test function you will need to select, so that the algebra becomes simple and it results in a simpler dynamics and all that actually. So, one idea turns out to mind that, okay, whenever you see an integral and all that, why not trying out the delta functions? Okay. If you try out the delta function, again, if you put this, one of the function happens to be delta function, then the entire integral happens to be just the function value basically. Okay. Sometimes people, I mean, define this without this 1 over t is not there. And if you have one of that as something like a delta function, okay, delta of t minus tn actually. Okay. Then what happens, the entire integral evaluation turns out to be just f1 of tn. If the only condition is tn has to be strictly lying between this interval actually. If it is one of the interval points, then it has to be half of that actually. Okay. Anyway, but assuming that tn is strictly inside this integral 0 to t, then the evaluation of the integral happens to be very easy, and the residual happens to be the residual value at that point of time actually, tn. So, this is the whole idea there, and then it brings in further simplicity and all that. Now, coming to the second point, how do you select the grid points? And this is a very nice demonstration I have taken from most of the lecture I have taken from this material, which this is a short course in IIAGNC, which I attended myself. Some of the materials I have taken from that side to demonstrate it actually. Anyway, so this is a very nice thing here happening. So, if you see this function here and then just put uniform grid points, then what happens here is it is not happening. In other words, it happens up to this grid point, let us say. So, in the center it is okay, because whatever value you are getting it there anyway. But the function value of matches within that interval also. Whatever points you are not seeing within that, there also the error is small actually within this period, I mean the time interval. But as you go towards the boundary, the function value is very different, even though the grid point value is same. So, there is some sort of a aliasing or illusion rather basically. Okay. That means, the value, grid point value is same as the function value, but in between the grid point there is a large departure actually. So, obviously, this is not a good function approximation actually. But if you take the same function and then do this, do this non-uniform grid point and things like that, you will have lot better advantage actually. Okay. So, these grid points which are really non-uniformly located are typically called as grid of collocation points, or normally grid points you can, so in a very loose sense you can call that way. So, these are typically done in a very non-uniform sense. It is something close here, something close here, something maybe sparse here, things like that actually. Depending on, there are several approaches again basically. Okay. So, anyway, so this is what you see here, and then what the literature claims that you have this, there are several ways of selecting that. There are something like uniform, then there is a Gauss grid point, then there are Gauss-Radau grid points, Gauss-Lobato grid points, various things available in the math literature actually. And it turns out that uniform grid point is not good, because whether you have 3 endpoints or 1 endpoint fixed or arbitrary endpoints, nowhere it is approximating in a good way. But if you slowly increase this, like you go to Gauss-Radau and Gauss-Lobato, then it turns out that Gauss-Lobato points will do a much better job in everywhere actually. Okay. So now the recommendation always is go towards this Gauss-Lobato points actually. The exact formulas of that is always available in the literature. You can see it very clearly basically. Alright, so Gauss is slightly better, but don't stop at the Gauss level, but go towards the Gauss-Lobato point sort of thing. Okay. Alright, so now coming back to approximation of the differential equation, here is something that we need to really understand actually. Let us assume that we have we have selected the this one, we have selected the basis functions, we have approximated that way, and we have selected the grid points also. Okay, now what actually? So what we are looking for is approximation of the differential equation. So we have this state equation and control equation that way, and then equation constraints will tell us, okay, these are the constraints what is happening here. So I will put it, I mean approximate value I will put it here, whatever I am approximating I will put it here, the dot, or that dot, remember this is the only function of time, this is a constant actually. So this dot will reflect in this dot really, okay. And then we have this quantity in the right hand side. Now if you multiply with delta functions on both sides, then what happens is this fellow happens to be some sort of a number, and then you will end up with these coefficients only basically. Okay. Now let us see that in a little bit more elaborate sense. Let us take some sort of something like a Chebyshev polynomial and confine ourselves to like 5 grid points only, just to have this clarity of our idea basically. So we have this grid. I mean, the nice thing about it is first 2 things you have to write, and the subsequent things you can write recursively. Ultimately, like it happens to be like this basically. Okay. Now what happens is x hat of t. Let's say we assume expand it this way. Okay. Right, and b hat is also, I mean u hat is also expanded that way. So we are not telling that explicitly here. But then x dot of t, when you do that, then it is like t dot here, t1 dot, t2 dot, because a0, a1, a2, these are all constant quantities actually. Now the good thing is this quantities, once it is evaluated at a grid point, it happens to be a number basically. So if I look at this equation and at a particular grid point, let's say some 0 grid point or whatever it is, 0 is something like this, okay, because these are now numbers actually. Okay. Similarly, x hat of t1 happens to be all these are numbers, and these are the coefficients which are typically unknown. So what will happen? In the left hand side you will have a differentiation matrix in the form of these, okay, but these are all numbers now, okay, t1, t2, t3 are all grid points now basically, okay. And right hand side is also a number, because ultimately you have this grid point values are available basically, right. So once the grid point values are available, those have become some sort of numbers that are known. What are unknown is something like coefficients a0 to a4 and b0 to b4. So this essentially, even though it is a differential equation constraint, it results into some sort of a algebraic constraint in the form of parameters actually. Okay. So if you consider the problem to be kind of unknown function in terms of a0 to a4 and b0 to b4, and this happens to be some sort of algebraic constraint in the form of coefficient. In fact, everything happens in the form of coefficients now actually. Now the last one, how do you do this discretization of the integral equation? You can do that trapezoidal rule, but there are much better ways of doing that, which is something like quadrature rule, and that is nothing but an approximation of the definite integral function, usually expressed as something like a weighted sum, where the wi's can be computed appropriately depending on what kind of quadrature rule you are talking about actually. Okay. So ultimately it results in some sort of a discretization of the cost function also, because that is what we will need for the static optimization problem actually. So we have got a algebraic constraint which is converted into it has taken care of the state equation constraint, and here it is something that will take care of the cost function. Other things are fairly straightforward direct actually. So finally what we have is something like a discretized version of the same problem, which talks about this minimizing this cost function subject to this set of algebraic equation now with endpoint conditions and path constraints. So, this problem can be, this optimal control problem has been now simplified to a lower dimensional nonlinear problem, nonlinear programming problem, and hence you can talk about some sort of a nonlinear programming problem, solution techniques and all that, which you can use to solve this problem actually. Alright, so this is now to demonstrate in a small toy problem first, and then we will solve it as a good application problem and wind up this lecture actually. Okay, first this toy problem, we want to minimize this control u square from 0 to 1 subject to this linear dynamics x dot is x plus u basically with the boundary conditions like this, and the control happens to control constraint is given, the modulus cannot exceed 1 actually. Okay. Now, this trivial toy problem is something which interests me in a different sense. If you really look at this is a quadratic cost function with linear state equation and all that. You can actually go and scalar problem also that too. So, we can actually go back to the closed forms equation, whatever we know already, okay. Assuming that this constraint is not there, let's say, you see that actually. Assuming that this additional constraint is not there, you can actually go back to EL equation or whatever equation we already know before, try to solve this problem. And interestingly, it turns out that the solution is nothing but u equal to 0 throughout basically. So, if u equal to 0 throughout, that means no control, the homogeneous solution happens to be the optimal solution for this, and u is 0, obviously cost function is 0 also basically. That is the best thing that you can also always have, without applying any control you will be able to do the job actually. But remember, this is an unstable problem, x dot is x dot equal to x plus x is actually an unstable problem. The trajectory will evolve in an unstable sense actually. Okay. This is time, this is x. What you are telling is the initial condition is 1 and the final condition at t equal to 1, this is our final time. Initial condition is 1 and final time it has to go and go to e actually. Okay. This is natural logarithm value, okay, e. And you can see this solution, if I take u equal to 0, I will end up with this, and this particular differential equation has a nice solution. Directly you can see that x of t is nothing but e to the power t into x of 0, but x of 0 is 1. So, this is e to the power t. So, when t equal to 1, then it is nothing but e when t equal to 1. Okay. So, we already satisfy the other boundary condition also, x equal to 1 is nothing but t. So, these are all validation sort of arguments actually. Okay. So, finally, what you are looking for is we try to solve this optimal control in a discretized manner using pseudospectral, but ultimately you know the solution, and the question is whether you are approaching towards that solution actually. So, here you can take Chebyshev polynomial of first kind, there are second kind and things like that, but you have taken first kind, and you see these are also kind of polynomial expressions, but in a different sense actually. Okay. Each of the basis functions are different sort of polynomials themselves basically. Okay. Essentially, but if you put them together, essentially it is nothing but a power series basically. Anyway, you can use this and then try to go ahead and then see this shift is okay. One is Chebyshev polynomial first kind, other one is shifted Chebyshev polynomial for the interval this, that and all. So, details you can see that in typically a math book actually. And the collocation grid points have been defined something like that. Remember, all these things, whatever you are talking, I forgot to tell one point probably that, okay, let me summarize it again. If I, okay, here we talk about 0 to T0 to TF, but the entire quadrature rule, grid point selection, all that will talk about something like -1 to +1. So, this scaling is necessary to make it compatible with that actually. So, that is why the scaling is put here, this a plus b by 2 plus a minus b by 2 sort of thing. Okay. So, these are the grid points, grid point 1, 2, 3, 4. So, you see how these things are sparse, these are slightly closer to each other, but these are farther away actually. So, like that. Okay. Then you have this state and control approximated like this polynomial thing. And if you see that d by dt of these, okay, it turns out to be something like this actually. Okay, you find out the differentiation matrix and equate the state equation at the grid point sort of thing. And then compute the Tn matrix, something like this Ti and equate the state equation. All sort of things we have is the inverse of that actually, T into D and then we put it there. This constraint, what you see here can be approximated something like this actually. Sorry, this dot equation and all that actually. So again, I don't want to go step by step here, but I think you can, knowing the concept, we can easily derive some of these actually. I suggest that you do it yourself also. Okay. So ultimately the constraint equation turns out to be something like this actually. Now apply the boundary condition. So we apply all these grid point condition, boundary condition, all that, whatever we know here. So ultimately this gives us this constraint equation that okay, these two constraints have to be satisfied actually, initial condition and final condition. Okay. Now this discretization of the cost function. So we discretize that way where W's are selected as something like this. All these numbers are given here, and then it results in a discretized cost function actually. Okay. So finally, we have this cost function to optimize subject to these conditions what you have here, and define the augmented cost function and things like that, and then we can apply this KKT condition, Karus-Kuntaker condition, or any other static optimization technique, numerical optimization technique and things like that to solve this optimal control problem actually. Now the solution turns out to be very close to what we expect. It starts with 1 and then 1 here like that, but once you put back the solution form, remember the solution is a polynomial actually, ultimately the solution is a polynomial. What you are solving for is the coefficients n and bn. What we already know is the basis functions Tn actually. So once you know the coefficients, actually we know the solution all over actually. Now one idea is, okay, we know the solution for control, you know the initial condition for the state, so you can integrate it using RK4 and then you get a different sequence of numbers, and those sequence of numbers have to fall on this polynomial what you know actually. Okay, so that's a validation technique. So let's assume that okay, that exercise is done actually in a good way. Okay, so anyway, so coming back to that, this is what it is. The numbers that you are getting is for the grid points, but associated with that, we also have a polynomial solution for this, and it happens to be very closely there with respect to the exact solution actually. Okay, one is interpolated solution, one is collocation point, and one is exact solution. So all the things are together actually. So that gives us a lot of good confidence there. What about control? Remember, these are numerical techniques. So 0 is not really exactly 0, but the number turns out to be something like 10 to the power minus 3, which is very small, very close to 0 actually. Okay, and that's why it is not disturbing the solution nature basically. Alright, so that is some sort of confidence for going further. And then what we do is we went to a little bit more realistic problem, or something called front to back turning of an air launched missile using pseudospectral method. So let's say how do you do that and what's the problem and things like that for rest of the time that I have actually. So this reference actually we have recently kind of presented this in this IFAC workshop which was done in Bangalore, right here in IISc actually. Anyway, this is the problem where you have a carrier aircraft taking a missile. Now typically what happens is this aircraft and whatever missiles they carry, they are all front looking. That means any target that appears in the front side, they can be launched and they can be engaged actually. But what happens, some target appears in the back, then the whole idea of dogfight comes into picture. That means this aircraft can increase its angle of attack, so it increases its lift, let's say, and then it also has more drag, so the speed comes down. It goes up with a lesser speed. By that time this goes front and then it does the reverse maneuver, and that means angle of attack it reduces, it comes down again, and so roughly it kind of it becomes behind the target. And the maneuver that you are talking about, first going up and then coming down and things like that, this is nothing but a cobra maneuver. So these are typical terms used in the air combat scenario sort of thing actually. Alright, so but that takes a lot of time. First you have to go up and then increase your angle of attack, go up, reduce, come back, and then align yourself so that you look at the target in front of you actually. So by that time target is not passive, it is also looking at you. You are remember for the target, if it is also happens to be an aircraft and all that in a dogfight scenario, you are already in front of him. Okay, that means this target has an advantage of firing towards the aircraft rather than we getting an advantage to fire towards the target actually. So the problem happens then that okay, can I really not launch a missile here? After all, that's also an aerospace vehicle. with larger capability, because aircraft turning is much lesser capability compared to the missile turning basically. So, this is larger turning capability. So, I will launch it and then quickly turn it backwards. So, that now I can the missile faces the target and hence it is it's equivalent to like a front attack basically. So, the problem here is how to turn this from the turn this vehicle from front side frontward going to the backward going sort of thing. Okay. In other words, the problem is to reverse the flight path angle from around 0 degree to something like minus 180 degree in minimum time. Okay. You cannot take too much of time to do the job also, because in a real combat scenario, time is everything actually. So, we turn it very quickly and then the turning problem ends here. After that, it can be guided in a different sense actually. Okay. And also remember, by the time it turns, it cannot take too much of induced drag. Turning also excites this induced drag concepts and all that. Any amount of turning has this penalty of induced drag. So, it should not have too much of that. So, ultimately what the constraint is, when gamma goes to minus 180 degree, it should also have some desired final Mach number basically. Okay. So, that you can still continue to move towards that actually. Okay. So, the problem is something like that, minimize this 0 to TF difference. So, minimize this cost function subject to the constraint that initial gamma is around 0, final gamma is minus 180, initial Mach number is known and final Mach number let us say equal to 0.8, hard constraint actually. Okay. The problem is to reverse the flight path angle from 0 to minus 180, maintaining the final Mach number of 0.1, 0.8 and it has to be done in minimum time actually. Okay. So, the system dynamics is first, and we see that the vehicle once it is launched, it has to go this kind of a thing. So, we have this dynamics in this scenario, we have some gamma coming here and some alpha and things like that. So, and also there is a thrust deflection angle that you are assuming. Okay. The thrust is not happening in the body direction, it has to happen some sort of a different angle direction sort of thing that can be done typically through various mechanism of thrust deflection, can be some SITVC, side injection thrust vector control, or maybe some fin deflection at the end, something like that actually, or there can be jet vanes or whatever it is actually. Okay. Some mechanism exists so that the thrust can be deflected. So, that actually augments to the angle of attack turning basically. Thrust vector is a much more powerful vector. So, if it turns, then the vehicle turns very quickly also basically in a way. And typically these are not restricted to very low degrees also. Thrust deflection angle that you are talking here can be a little bit higher than the alpha bounds and all that way. Anyway, so you have this point mass equation V dot gamma dot S dot and X dot. So, these two represent dynamic level equation, these two represent kinematic equations like that. Everything happens in 2D sense here. Then following this reference, okay, the idea here is to non-dimensionalize the entire problem, okay, so that the problem can be more and more generic actually. So, we take care of that. First we normalize, they define these non-dimensional quantities, and starting from this we actually write this equation. Now, m prime means del m by del tau basically, okay, where tau is defined something like this. So, we write it the same system dynamics in non-dimensional quantities something like this, and then remember this is a difficult problem because we do not want to excite this bang control and things like that actually, that is open loop control actually that way. So, we have to again going by this idea which appeared here in this literature, the idea here is to convert this free final time problem to some sort of a state constraint problem with bounds on control, and then equation of motion are formulated using flight path angle as independent variable basically. Okay. What you are assuming here is the turning happens in one direction only, that means the flight path angle is monotonic actually. So, if you assume that then you can take the flight path angle as independent variable, and this leads to this fixed final condition where it talks the initial condition of gamma I know and final condition is minus 180 degree. So, it happens to be a fixed final condition now actually, for fixed final time sort of thing now actually that way. Okay. So, that becomes amenable for solutions using this finite time optimal control theory basically that way. So, the entire assumption boils down to that okay, flight path angle is monotonic and continuous function with respect to time. So, that is the inherent assumption based on which can attempt to solve this problem. So, now when gamma is independent quantity, we have to assume this first define this dm by d gamma is something like m prime by gamma prime, dt by d gamma 1 by gamma prime, like that actually. And then you have this modified cost function is something given like this, 0 to Tf is equivalently written as something like d gamma, integration of d gamma. But d gamma, it is something like dt has to be converted to d gamma. So, dt by d gamma, but then this is 1 over d gamma by dt and things like that. So, d gamma by dt is available from here. So, put it back here. So, j is available as some sort of a complex function, but ultimately it is time minimizing cost function actually. Okay. And then there is a hard constraint. So, m of gamma f has to be 0.8 actually. Then you go through this long algebra of discretized mathematics to minimize this cost function, quadrature rule, okay, subject to this derivative approximation, subject to this equality constraint equation, subject to this path constraint also, that alpha cannot be more than 20 degree and delta cannot be more than 72 degree. That is what I told, delta can be much more than the alpha basically. Okay. So, and essentially when these endpoint conditions are direct, okay, m0 can be anywhere between 0.3 to 0.8, however, mf has to be 0.8, that is the problem actually. So, these are some of the experiments you tried out with various different cases and all that. So, remember, no matter whatever is the initial condition of Mach number, the final Mach number turns out to be 0.8 actually. Okay, so, this is a very nice observation, first thing to see. And if you see the kind of height versus down range sort of thing, this is the trajectory that you see. So, this is launched from somewhere here and it all turns out, I mean, it nicely turns where you want actually. The turning happens nicely basically. Okay. Then you have this angle of attack constraint, which is also more than 20 is not allowed, something like that. This constraint is coming into picture. So, that is enforced here. Okay. And this is all within the bound actually. Whereas, delta B, which is also this thrust control mechanism sort of thing, this is actually helping that to remain within the bound actually. Okay. So, delta B turns out to be like this, all are smooth trajectories, see that also. And then the point here is the final Mach number is 0.8 no matter where you start. So, velocity drop is not there actually. Okay. Then the Mach number versus angle of attack, something like Mach number versus flight path, and angle of attack versus flight path, all the things you can plot in different variable sense and has a lot of more meaning actually. Okay. And remember, this has to be seen from the right to left actually. No matter what you start, you all end at the 0.8. Flight path angle evolves from 0 to minus 180 degrees. So, these plots have to be seen in the reverse, right to left sense actually. Okay. This also has to be seen in right to left sense, angle of attack, how it evolves as the trajectory. Flight path angle per time, how it evolves actually, then this always has this 0 to minus 180, but depending on different cases, different things are there. How do you generate this plot by the way? Because once flight path angle becomes independent quantity, okay, then time becomes some sort of a state equation. So, dt by d gamma equation is also put into the problem formulation. So, corresponding to a particular gamma, you have the corresponding value of time actually. So, both cannot be independent quantities, only one has to be independent quantity. So, according to that, the other one varies actually. So, that is how the time is generated and it is plotted something like this here. Okay. So, now we can think of effect of reducing angle of attack and things like that. So, this depends on the shear angle again. If this is more, that can be less and things like that actually. Okay. Okay. Now this, okay, what is shear angle and body angle? Some of these things are aerodynamic concepts. You can see this is with respect to the body, this is the body angle delta B, and with respect to the velocity vector, this is a different angle, that is shear angle actually. Velocity vector and thrust vector, that is the shear angle. That can be even higher than the body actually, according to the diagram. Okay. Alright, so this is what it is actually. Then effect of the reducing the angle of attack along with the flight path. I mean, all details are there in the paper. You can read some of the explanations there also. So, let me not too much elaborate here, it is all happening in a good sense. You can plot flight path versus time, how it evolves, and plot Mach number versus time, how it goes from 0.5 to 0.8, depending on different cases actually. Okay. That means we put various bounds on alpha. We have this initial bound is some 20 degree. Now we put various bounds on that, and depending on that, the other things get streamed out actually. Now the question is how it's a function of grid points now. So initially you start with the coarse grid, 5 grid points only. Not good. You can see some of these things are bad looking sort of things. But then once you have this history in place, you can use that as a guess history and then go for finer grid and all that actually. So, find 5 to 10, 10 to 12, 12 to 20, 20 to 30 like that. Now, you can observe that beyond 20 there is not much of not much of an issue. So, going beyond 20 is no point actually. Okay. So, we take that 20 grid points are good enough for the solution, and we leave with the 20 grid point solution basically. Okay. You can see the number of grid points versus computational time and all that. So, if you have 5, obviously your computational time is very small. They are all evaluated in this hardware settings, which is a regular desktop with MATLAB 7.4 running and all that. It is not a dedicated processor. Okay, the whole idea is if you have a real-time onboard processor with a dedicated processor, all that, this and your program is written in terms of machine learning language, then it can be much faster than that actually. Alright, so but even this setting, we have this 5 number of grid points being 5, this is the computational time. Then 10, 12, 20, it starts increasing, but beyond a point is not, so beyond 20 we don't recommend, so we freeze it here actually. So, the real time implementation in C or assembly language is expected to be much faster, and hence it is, we think that can implemented in real time actually. Okay. Now, what was the idea of Chebyshev versus Legendre? It turns out that you take Chebyshev polynomial or Legendre polynomial, both happens to be like giving us the same result actually. So, there is one way or other, there is no advantages per se basically. That exercise tells that. Okay, so this is another consistency check also. You can think about that actually. So conclusions for the missile turning problem is like this. The real hemisphere engagement is feasible. So physically speaking, there is no need of dogfight. Provided, of course, you can implement this high shear angle values and all that. Okay, this values what you are seeing here, bodies delta V or shear angle, so thrust control augmentation, that has to be implemented. Now, that has to be seen. Subject to that condition, it is possible to have this conclusion basically. Minimum time flight path angle reversal is feasible with realistic control force. That's what we think. And then promising numerical results, that means computationally they are efficient and a viable tool for optimal guidance per se, and Chebyshev Legendre polynomial lead to the identical results actually. So, this gives some degree of confidence that pseudospectral method can be used in various applications. As I told before, there are various other things that Michael Ross, I.M. Ross and his group have actually demonstrated. There are other groups also working on the pseudospectral method, but this team has actually demonstrated to a variety of problems and including hardware implementation and implementation in International Space Station also. So, some of these references you can see for more details, and my recommendation will be probably the first one, okay, which appeared very recently 2012 with some sort of a very good overview of the method itself, okay, and from theory to flight and all that actually. Okay, so if you can read some of these papers, it's also written in a way that is not too much mathematically involved, whereas other papers can be a little bit math overwhelming also basically. This is very intuitively written, very relatively long paper, and summarizes the concept in a necessary mathematics sense and all that actually. So, my strong recommendation is that you should read this paper and understand more actually. Alright, so this is what I wanted to talk in this particular lecture. Furthermore, on that what we have developed on these ideas and all that, calling this MPSP method and MPSC subsequent things and things like that, we will discuss in the next lecture actually. Alright, thanks a lot.